Well, it's a real treat to be here, and hopefully when I'm done, none of you will want to say that this is way above your pay grade. One of our themes in our physics and astronomy department here at Clemson is that physics is for everybody, and this is for everybody as well. In fact, one of the most rewarding areas of study in astronomy is understanding how you go about forming planets around young stars. Going back just, 200-300 years ago, scientists were already proposing, hypothesizing, that planets form from the detritus of star formation. Over the last 25 years, we've seen this amazing advance in our understanding of this entire process. But as much progress as we've made, there are a lot of questions that remain unanswered. Part of the reason for that is it remains incredibly difficult, frustratingly difficult to actually see these forming planets. Our detection of forming planets remain few and far between. In fact, I'll show you one of the cases. In fact, it's the only case. So what I want to talk about this morning is, one, why is it so hard? Why is it so difficult to detect a forming planet? Second, what are we doing about it? How are we going to go about solving this problem? And third, why should we care? And finally, why am I holding a grapefruit while I'm doing all of this? Well, part of the thing about astronomy is that we deal with really vast scales, unimaginably scales. You might even call them astronomical. Bad. So imagine for a moment that the sun was a grapefruit, the size of a grapefruit. If the sun was something about this size, the Earth would be about the size of the ball in this ballpoint pen. You guys see that? Yeah, me either. I don't have my bifocals on. Jupiter would be about the size of this coffee bean, and it'd be about 1 million times fainter than the sun. This ball in the ballpoint pen would be about 10 meters away from this grapefruit. And this coffee bean would be about half a football field away, about 50 meters or so. The next grapefruit in the entire universe would be about 2,000 kilometers away. In other words, if I was in Fargo, North Dakota with this grapefruit, the next one would be in New Orleans, Louisiana. That's the kind of scale that we're talking about. But this is just another star. If we want to see forming planets, we need to look at a forming star, something that's very young. Planets form along with the stars. And the nearest star-forming region would be on the moon. So if the sun was a grapefruit in North Dakota, the nearest star-forming region where we'd have a shot at seeing a forming planet would be on the moon. So we'd be looking on the moon around something this size, for something about this size, about 50 meters away, that's 1 million times fainter. That's hard. So as my hand's getting kind of warm holding the sun, so I'm going to toss it over here. Hopefully I won't burn the building down. Don't tell the fire marshal. So to put this all into context, I want to say just a few words about star formation and planet formation. And one of the dangers that we scientists fall into sometimes is getting into some jargon and confusing everyone with words that don't mean the same thing in science that they mean when we're talking in the real world. And so the whole process of planet formation starts with the death of stars. And as these stars die, they expel gas and dust, and that gas and dust agglomerates in the Milky Way galaxy and forms these dark lanes that you see in the Milky Way here. And in those dark lanes, if we zoom into one of those dark lanes and blow it up, what we see are these star formation regions. Now, the image on your left is an actual photograph taken within a telescope, in this case, the Hubble Space Telescope. The image on the right is the work of a brilliant graphic designer, me. And what you're seeing here are forming stars. Now, they don't look like stars. The reason for that is they're enshrouded in dust. And so if we zoom in to that region where the core of that region is, as that surrounding material dissipates, what we see is a disk, literally a disk, around the star. And it looks something like this. And so as we're looking at this, what we're seeing is a disk around a forming star. Again, an actual image, real-life image taken with a telescope on the left, artist's impression on the right. And that's why we call it a disk. And what you're seeing in those gaps, the reason there's those rings there is that there's planets forming in those gaps. You see the planets? Yeah, no, neither does anybody else. We don't see the planets. What we see is their wake. Have you ever been on a flight that's taken off from an airport near the bay, near a body of water, and as you're taking off and you look out your window and you look down at the water, you might see some streaks in the water. And those streaks, the wakes, you might not see the boats, but you can see the streaks. It's kind of the same thing. It might look something like this. You guys can all see this wake, right? But the boat is really hard to see. Some of you in the front may see it, some of you in the back maybe not. That's why it's so difficult to detect. That planet, that tiny planet, something the size of a coffee bean, is plowing through this gas and dust and creating this wake, and that's what we observe. And so I'm showing actual data here and models, computer simulations of the process on the right. And part of what's holding us back in really understanding how planets form is the challenge we face in actually seeing those planets. Again, we're looking for something the size of a coffee bean, circling something the size of a grapefruit 50 meters away on the moon. And this coffee bean's 1,000,000 times fainter than the thing that is flying around. And so this is the challenge that we face, but we're making progress. We have examples of this. Of all the disks we've looked at, this is one where we've actually seen this process happening, this process unfolding. And so these telescopes, the ALMA array is pointed at this forming star, and what it sees are these blobs, and these blobs are baby planets. We finally have one example of this happening. Why is this so difficult? Well, it's because these forming planets are tiny, 10 milliarcseconds, at MAS, milliarcseconds. We all know what a milliarcsecond is, right? Yeah, maybe not. So what is a milliarcsecond? If you were an astronaut on the moon looking at Earth, a toddler on the Earth would subtend about 10 milliarcseconds. And so that's what you're looking for when you see this. But the other thing I keep mentioning is how faint these planets are compared to their stars. They're really hard to see. And that's mostly true, but not entirely. Because see, as the gas and dust swirling around the star agglomerates into a planet, it doesn't go directly onto the planet, it forms a disk around the planet itself. And the planet supports that disk, but eventually so much mass piles up into that disk, it looks something like this. That material builds up and builds up and builds up, and eventually it comes crashing down on the planet. And when it does that, it releases all kinds of heat. And it gets really hot and really bright, and we have a shot at seeing it. Problem solved, right? But here's the thing. It takes thousands of years for that material to build up, and something like years for it to come crashing down on the planet. Which means if you're looking for an example of this, you're looking for something that happens 1 in 1,000 times. That means you need lots of disks to look for these baby planets. And that's kind of tough too. So we have an example of this, but there's a trick we can play. When I say that it cools off quickly, what cools off quickly is the dust. The dust and the gas don't cool at the same rate. And so astronomers refer to something called blackbody radiation. And what I'm plotting here is a slide showing the radiation emitted by a solid. And on the y-axis, that's how fast it's radiating its energy away. And what that tells you is how bright something is. And on the x-axis, we have the wavelength of the light being emitted. The light we see with our eyes is the rainbow there. And so all of that, the area under that curve is how quickly the dust is cooling off. Now, if you squint, you might see some black lines on this plot. Those black lines are a spectrum of gas. The area under that is how fast the gas cools off. And you don't have to be an expert in calculus to realize that the area covered by those little black lines is a lot smaller than the area covered by that solid curve. And so for that reason, the gas stays hot a lot longer than the dust does. So if we can look for the gas coming from that circumplanetary disk, we have a real shot at seeing it. There's another effect that we can take advantage of, and that's the Doppler effect. As something moves towards you or moves away from you, it can be Doppler shifted. All of you have experienced it. If you've ever sat in traffic and had a police officer or a fire truck or an ambulance come behind you with its sirens on, you may have noticed as it's coming towards you, it's high-pitched, and as it passes you and you breathe that sigh of relief, they're not pulling you over, it's kind of low-pitched. That's the Doppler shift. So what happens with sound happens with light. And so when the light's moving away from you, it's shifted to the red, and when it's coming towards you, it's shifted to the blue. And so that process, we can go and see the planet moving by measuring the shift in these lines. And so we've done exactly that. We have an example where we've done that. We have a forming planet in a disk, and we see these lines shift. And I've put the years of the observations when we took this data. And you might notice that the first observation was in 2003. I was a graduate student then. The final observation was in 2017. I was the department chair of physics and astronomy at Clemson by that point. My point is it takes a long time to get this data and to observe that. And so if you want to do this with a lot of systems and you want to follow it over multiple orbits maybe, it's going to take a lot longer than one person's career. And so to make advances here, one of the things we need to do is save that data and pass it on and share it with other people. And that's exactly what we're doing. We're creating databases. We're in the age of big data now. And so when one person collects this data, it doesn't stay on just their hard drive. It's shared with the entire world. And so all of you could go to this website and download the data from all of these stars and play with it yourself. And then any astronomer who collects that data can put it into the same database. The other thing that we want to do is build bigger telescopes. The telescope I used to collect the data I just showed you had an 8-meter mirror. So the mirror that's collecting the light was about 8 meters in diameter. That's a really big telescope, a lot bigger than the kind of telescope you might use in your backyard. But we're moving into the age of the 30-meter telescope. As I'm giving this talk, we're building telescopes that'll have mirrors 30 meters in diameter. And so why does this matter? It'll allow us to see 10 times as many of these systems, so we have a better shot at catching them while they're undergoing their outburst and when they're in a bright state. And so the interplay between technological development and better ways of storing data and sharing data and so forth is driving forward our ability to see forming planets. Now, when I started this talk, one of the things I mentioned was the vastness of space. Again, if the sun was a grapefruit, the Earth is the size of the ball in this ballpoint pen. And the nearest star-forming region would be on the moon. Why should we care about any of this? There's no hope of any of us, or our children or our grandchildren, of ever visiting one of these planets. What does it matter? This is a question I often get when I give talks or when I teach astronomy class to students. Why does any of this matter? And the answer you might hear is spin-off technology. People talk about the sort of things that come out of this. You know, we put a person on the moon, and what did we get out of it? Tang. But to put it that way is to really undersell why we do basic science. To be sure, there's a very rich history of basic science driving technological development, but that's not really the reason that we do this. One of the architects of modern physics, Henri Poincaré, pointed out that over 100 years ago that making the case for science based on driving technology is really to undersell what we're doing, because the real reason we pursue science is because it raises us above ourselves. As I talk about the immensity of space, it becomes pretty clear how puny and insignificant the human body is. We're just a tiny speck on a tiny speck around a tiny speck in a small corner of a galaxy that's just a tiny speck in the local group, which is just a tiny group. I mean, lots of tinies here are piling up. On the other hand, what astronomy takes away, it gives back so much more, because it illustrates the power of our intellect to take in the whole of this dazzling immensity of the universe. And that whole implies with it the importance of us not squandering that power of the human mind. Thank you all.